Oh, there we go.
Sorry about that.
I can start again if you like. Why don't I do that for the recording? Okay,
That would be really great. Thank you, John.
no problem. So today we're going to be looking at sedimentary structures, and it's a huge topic. We're just going to scratch the surface today, but I think they're important because they are probably the most powerful tool when you're reconstructing ancient depositional settings. Sedimentary structures occur on a wide variety of scales. The biggest sedimentary structure in the world is a Triassic delta, which covers 1 million square kilometers. And the smallest sedimentary structures you can literally look at on a thin section. So that they occur at all scales. And the pictures on the right here are showing a Cretaceous fluvial channel. Then we're zooming in to look at one particular bed and then looking at the actual cross beds within that bed. So you can see there's a lot of different scales that we'll be dealing with today. Sedimentary structures fall into depositional, deformational, and erosional characters. So depositional ones are ones that build up sediment. Deformational is when those rocks are folded, and then erosional is when you have scouring down into those beds. And the structures that we're going to look at today, how they present themselves in the fossil record depends on a whole variety of factors. And some of those factors include the amount of space that the sediment has to fill up, the energy levels, so how fast the flow of water is, the grain size, roundness, and abundance of the sediment that you have to be able to deposit these structures, the water depth or lack of it. You may not have water, you may be in a terrestrial setting, and then whether your currents flow in one direction or whether they are variable through time. So what we're going to do today is to go through the main depositional environments from proximal to distal, so from fluvial all the way out into the deep sea, and we're going to look at the different sedimentary structures that you might encounter in those environments. And I'll be showing these green boxes as we go through, and inside the green boxes will be the recognition criteria, the criteria that help you to identify each of those sedimentary structures. We're going to see some structures in core as well and a few trace fossils, but today's talk is not about trace fossils. If you want to know about those, I'll have to talk about those on another day. So the depositional settings that we're going to be looking at range from fluvial up in the mountains. So if we look at this top diagram here, we're river sediments, lake sediments. We're going to look at some aeolian, so wind-blown desert sediments down here at the bottom. We're going to go into beach, delta, and estuary environments, estuarine, and then out into shallow marine conditions. And then finally, we're going to go down the paleoslope and down into deep marine conditions. We're going to focus in on clastic deposits today, so sand and mud dominated, but all of these structures can also be found in carbonate rocks. So they're just a little bit more difficult to see normally because of the whiteness of the limestones or the light gray color of the limestones. But trust me, every structure that we're going to see today is also present in carbonate rocks. This is a very important diagram, which just talks a little bit about grain size and what currents you need to move it. So obviously, if you've got very slow moving currents, they are not going to move gravel around. So they're not going to be able to move gravel. But if you have a fast moving current, then that can move sediment around very easily. So on the bottom left here, we have a diagram which shows particles being transported. So fine grain particles, you can see low velocities, which is shown on the left-hand axis here. You don't need much velocity to move a clay, but you do need a lot more velocity to move something on the right-hand side of that diagram where it says boulders. You're going to need a very high velocity flow before you can move those. And then the diagram at the top right here, that diagram shows the kind of structures that you can expect. So if you have slow moving currents, so once again, we got current speed on the left here. Slow moving currents, we get ripples with fine grained sediments, and then we get no motion at all with coarser grained sediments. And then as you speed up your currents, you'll see that we create sand waves, dunes, upper plane bed flow, and then finally up into anti-dunes here. So the current compared to the grain size is very important in determining what kind of sedimentary structure you're going to see. So let's start off by talking about the basic building blocks, the most basic sedimentary structures of all. And we're going to start off with trough and planar crossbeds. So these are both dune-forming crossbeds. They are dune-forming sedimentary structures. And what happens in a typical case here is that on this diagram at the top right, we'll move these little particles here, which might be silt, they might be sand. They move up the dune and then they cascade down the dune front. And if they cascade down a straight-fronted dune, then you'll form planar crossbeds. And if they cascade down a curve-fronted dune, then they'll form trough cross beds. So if you look at the diagrams at the bottom there, you can see this is trough cross beds with sinuous crested dunes, and then we have planar crested dunes on the left here as well. And when you look at that on how it would look on a riverbed or a shallow seabed, you can see that you end up with these either planar dunes or you ended up with these curvy dunes as well. And these are really some of the most common depositional sedimentary structures that you're going to see in the fossil record. And we'll talk about these more as we go through. So this is some examples from the field. So we've got some planar cross beds up here, and the planar cross beds are definitely rarer than trough cross beds, certainly in dune form. So you can expect to see a lot more of the troughs. And then this diagram here, the lower photograph here is from trough cross beds here in Alberta. And what we can see if we look at the diagram on the right, the photograph on the right, is that you can see that trough cross beds they're curved. They're sloping down towards the bottom of the bed, and then they're soling out at the base of the bed. So they flatten out to the base of the bed. And what's nice about that is it means that if you have a rock that you don't know which way up it is, then you can tell which way up it is by looking to see where those beds flatten out at the base. So they're cut off at the top, they're eroded down, scoured into at the top of this bed, but at the bottom of the bed, they're soling out. I've got example here from the sky as well, because clouds are basically particles of water which are being moved by a current, which is the wind. And we can see here we have the same kind of curve-crested dunes sitting up here a couple of kilometers above the ground. And I took this photograph out of an aircraft window. So another very, very popular structure that you're going to see everywhere is ripples. And there are two kinds of ripples. There are other kinds as well, but the two main kinds are current ripples, created by flow in one direction, and wave ripples, which are created by oscillating flow, which you're going to see obviously at the coast. So with current ripples, you can see here from this pictorial sketch, they are asymmetric. So they have a flatter back end, steep front end. So they're like a little trough cross-bedded bed, actually. The sedimentary structures are basically the same. And when you have wave ripples, because the currents are going backwards and forwards, what you see is that you basically have a symmetrical. So this is symmetrical in wave ripples, asymmetrical in current ripples. So if you go into the field and you see some ripples like this, like we're showing on the lower left here in the photograph, you can say immediately they have a flat back and a steep front. So this is a current ripple, and the flow would be down towards the bottom left-hand part of the slide. We also see with the wave ripples that you can see interference patterns as well. So if you have very shallow conditions, and this is obviously on a beach, so with shallow conditions, you'll have currents coming from different directions, so you'll end up with interference patterns. So it won't be a simple wave pattern like in the middle here, but it will be a more complicated pattern that we see on the right-hand side instead. And once again, we see the same kind of ripple structures in the clouds as well, although obviously on rather different scale. And this is just a nice example here from the Paskapoo sandstone here in Calgary. And you can see really nice current ripples in here. Steep side over here, and then flatter side over here. So the flow would be towards the left-hand side of that photograph. Another very common structure, but one that isn't very well preserved on bedding planes is upper versus lower plane bed flow. So when you have currents moving very fast across a bedding plane, they're too fast to actually deposit anything. And what they do is they just leave a little streak of sediment behind them. And often the sediment streaks are very micaceous. The mica seems to be able to land on a certain spot and stay there. But I have to say that they're reading through the literature about these upper plane bed flows or primary current lineations, they're still relatively poorly understood. So what we do is you can see these streaks here, which will be showing the flow either up towards the top of the page or down towards the bottom. There are also lower plane bed flows. So this is one of those confusing things where you get the same structures in a very energetic setting and in a very low current setting as well. So lower plane bed flow is where you have currents that are so slow that they would generate ripples if you had finer grained sediments, but in coarse sediment, all they can do is make a slight lineation on the sediment. So they look the same, but generally they're much rarer. So what you should be looking for, if you see these kind of like streaks on a bedding plane, you can be fairly confident you've got a fast current and you're making primary current lineations. Once again, you see these in clouds as well. So what we're going to do now is that we're going to move on and move through the different depositional settings and talk about what sedimentary structures you might see and how you can use them to help you to understand what the depositional setting may be. And we're going to begin right at the back, right up against the mountains with alluvial fans. So alluvial fans are fan-shaped deposits of water-transported sediment. So you can see in this diagram on the top right, we have some mountains there, and then we have a little pass or a gap in the mountains, and the sediment is being washed out from there, very steep gradient. There's a break in slope here, and because of that break in slope, you lose energy and you start depositing. So the photograph here on the lower right is from Death Valley. It's a very famous bad water alluvial fan, and this is very close to one of the lowest points in the contiguous United States, on land in the States. This is actually below sea level sitting in here. With these kind of deposits, they tend to be coarse-grained, but maybe finer-grained at the edges. So you have coarser material in the core of the fan, and then as you go around the edges, you'll see finer-grained material as well. And they're usually poorly sorted, and they're usually very coarse as well. So if you're going to be looking for conglomerates and looking for pebbles, this is the place that you want to be looking for. So what we see here when we look at these in detail, and I've got some pictures here. I've got one from Death Valley, and I've got one from Budley Salterton down here on the Devon coast. It's quite a funny beach to go to, because when you take field trips there, you walk down onto the beach, and there's a big sign there saying clothing is optional beyond this point, because it's actually a nudist beach, because nudists are particularly interested in alluvial fan deposits, apparently. And when you go down onto the beach and you look at these sediments, what you can see here is that the pebbles are aligned. So if you look, hopefully you can see that there's a kind of fabric to these pebbles where they're all dipping down towards the left. So what happens is that you have a pebble sitting in the river, and if the pebble's leaning upstream, then eventually the current will start knocking it or flipping it over until it ends up in this position here. And the current comes along, and the current kind of like brushes off the top of the pebble. So you end up with all of the pebbles dipping upward towards the downstream direction. So what this would show, this photograph here, is that we have flow towards the right of the page. And the same thing with this, the picture on the left here, this mosaic from Death Valley, Mosaic Canyon in Death Valley. And then I put this picture in here at the bottom. This is from a project I'm working on at the moment in Calgary. And what we can see here is that the pebbles are actually dipping in the other direction. So the flow would be towards the left. And this is from a recent gravel deposit. So the way to identify these is that you're going to see imbricated pebbles showing the direction, thick conglomeratic beds, and often, because they are terrestrial deposits, they're going to be red in color as well. And we're going to see more red beds as we go through the presentation. Right. River deposits. So the river does, there are lots and lots of these fluvial deposits around the world. So they're a very important part of this presentation today. So when you look at rivers, sometimes the channels are very, very clear. And up at the top here, we've got a beautifully defined channel with a nice scoured base there. It's scouring down into overbank mudstones, and it's very easy to see. But more normally, what you see is stacked sandstones like this. There's some evidence of scouring here at the base of some of these sandstones, but you can also see that there's been a lot of activation, reactivation, channels cutting into one another, and it's a little bit more difficult. So in that case, where you can't see these lovely channels, then you might want to use other things like the sedimentary structures to tell you what's going on. And I did say we weren't going to talk too much about trace fossils, but I felt obliged to share this fossil here. This is a dinosaur footprint, a sauropod footprint that I found in December up on the Yorkshire coast. And those scratches down there, down the sides, are literally where the dinosaur's toes scraped down through the sand as it was walking across this river. And there's a 25 centimeter ruler there for scale, but beautiful trace fossil. So one of the other things that's important when you're looking at these channels is, why are these channels stacked up? And what this raises a huge question, brings up a big topic about changes in relative sea level. And if you may not be aware of this, but sea level changes through time. And right now, we are apparently in a phase where sea level is rising. So we have a rise in sea level, a transgressive sea level rise. But there have also been times in the fossil record where sea level has fallen. And how that sea level reacts and how it behaves, that helps to decide what's going to happen with your channel stacking patterns as well. So in this diagram on the right here, when we have a low stand, so when we have a fall in relative sea level, we have scouring, So the sea is way down now. The sea level's lower. There's a steeper gradient. So the rivers start cutting down a little bit like they've cut down into the Grand Canyon when the Grand Canyon was uplifted. And you end up with stacked channels here that we see in the bottom part of this diagram. But then as you raise sea level, you create more accommodation space. So there's more room for sediment to be deposited. And you end up with lots of the green stuff, which is the overbank deposits, and less of the channels. So the channels here are quite widely separated. So when you're looking at an outcrop, if there's lots of stacked rivers, you can be pretty sure it's a low relative sea level. If the river channels are quite isolated, high relative sea level. So we tend to divide rivers into three different classes. There's low sinuosity or braided channels. There's high sinuosity or meandering channels, and then there's the weird anastomosing channels, which I'm not going to talk about today because they make up less than 1% of the channels around the world. So what we see with a braided river or a low sinuosity river is that you have multiple channels with lots of bars, and they call these braid bars. So you can see this example here from modern New Zealand, where we have the channels flowing down with bars in between them. And if you were to look at a section through here and take a section through this channel, what you would see is something like this. So we've got stacked sand on sand on sand. And then at the very top of the river channel, we'll see some rippling up there at the top. But the rest of it is going to be dominated by trough cross bedding. So if you see trough cross bed on trough cross bed on trough cross bed, like this diagram here on the left, the photograph on the left, then you can be confident you're in a low sinuosity fluvial system. So the main sedimentary structures that you're going to see, as I mentioned on that cross section, is trough cross beds towards the base. And once again, we've got some troughs here. You can see them soling out onto the base of the channel here. And then we've got current ripples overlying them. So these are asymmetric ripples, which are capping the river, which would have been deposited towards the end of the flow when that channel was being abandoned. And then this is just one cross section through a Cretaceous channel that I logged. So what we've got here is mudstone underneath. That's in gray. The orange is trough cross bedded sands, and then it's capped by yellow ripple sands. And the length of this section is about 80 meters, and it's about 5 meters in thickness. So that really gives you a nice idea of how big that river was when those sediments were deposited. Now, meandering rivers are quite different. Why do you have meandering rivers? Well, what happens is that turbulence, while you have flow, will cause the river to bend. And you'll end up with flow being faster on the outside of the bend and slower on the inside of the bend. So on the inside of the bend, because the current's slower, you'll get deposition. So that builds out what's called a point bar. And on the outside of the bend, you have what's called a cut bank, where the river is eroding into that outer bank. And it's amazing. There's probably about 20 places in Alberta called cut bank, because they were all settled on the high ground next to the river, which would be on the cut bank side over here. So how would you recognize this deposit from what we just saw? So the one we just saw was those stacked trough cross beds. What we see in meandering rivers is that we have trough cross beds at the very base of the channel. So the flow is fast there, but then that will be overlain by point bar deposits. So these point bars here, so this will be slower flow. And what you'll see is that the successive locations of the bank, of the point bar bank, the gently dipping bank, will gradually build up over time. So you'll end up with a stack of either gently dipping sandy sediments, or if you have periodic fluctuations in flow, into beds of muds and sands. And those are called lateral accretion surfaces, if they're sandy, or LAS for short, and inclined heterolithic surfaces, or IHS, if they're made up of sands and muds. So all you have to remember is LAS or IHS. And when you go to an outcrop, you should be looking for those dipping surfaces if you think it's a fluvial deposit. So this is just some examples from the field. So here we have an example from the McMurray Formation. So this is actually from the oil sands. And what we can see is that we've got these nice dipping inclined heterolithic stratification, IHS, with sands interbedded with muds. And the muds do make things a bit more difficult when they're trying to produce the oil sands, because they act as barriers to flow of the oil. This is a slice up here at the top. So spectral decomposition, so seismic slice showing some of these oxbow lakes, some of these channels, which have been deposited in this overall sandy succession. And then over here, we have an example of what your succession should look like. We have channel lag at the bottom, trough cross beds, and then passing up into point bar deposits towards the top. And this picture here with my friend Krista for scale is from Dinosaur Provincial Park, and it's just showing one of these sets of lateral accretion surfaces sitting in here, dipping down towards the left-hand side. So that will be the direction that the river was migrating. So this is an absolutely classic example, also from Dinosaur Provincial Park, where we have, at the bottom I have just the photograph, the panoramic photograph, and at the bottom here I've interpreted it so you can see we have trough cross beds at the bottom. So this is the fast flowing part in yellow. Then we've overlain that by inclined heterolithic stratification, so this would be the point bar deposits, and then this particular river avulsed, so it cut through a neck, some kind of neck, and it flowed off in another direction, and then we were left here with an oxbow lake, and that oxbow lake is filled in with muds. So all of the mud there that you can see at the top is basically from an oxbow lake with the sandier sediments sitting underneath it. And then this is just the sketch at the bottom here is just to kind of summarize that. So we've got trough cross beds at the bottom, inclined heterolithic stratification here on the left, the right-hand side, and then we finish off filling it up with mud at the top. Also associated with rivers, we see crevasse splays, and these are where the river bursts its banks, and there's lots and lots of flooding. It seems like there's more flooding these days, possibly due to global warming, but either way, there's lots of reports of flooding in the news. And what happens when the river bursts its banks, it deposits sediment as well. And that sediment there, this white sediment that we see on the lower right, that is called a crevasse splay. And crevasse splay deposits are deposited very rapidly, so that this whole splay probably took less than a week to accumulate. And so because of that, because the flow is so fast and the sediment's accumulating so fast, you tend to get what are called climbing ripples. So the ripples are literally building up one on top of the other, rather than actually flowing along. The water is actually helping them just to build up through time. So these are climbing ripples here on the lower left. You can see that very nicely. The pattern here is the ripples are accumulating vertically upwards. Like I said, this happens probably over a week. And what we've seen in this diagram at the top right here is that we have the same kind of thing with these climbing ripples, but they've been colonized by beetles. And these are beetle burrows. There are some circular ones, and there are some burrows going down into the sediment. These are called Tinidium is their technical name. And these beetles are colonizing a crevasse splay deposit. So if you want to find crevasse splay deposits and identify them in the fossil record, look for those climbing ripples. This is by far the most likely place that you're going to see them. So just to summarize for the fluvial, by looking at some cores, the key features to identify trough cross beds is that they're all concave upwards or convex downwards. So they all have this smiley faces. And if you see those smiley faces and there's nothing going upwards, nothing doming upwards, then you're likely that you are in trough cross beds. And they will all soul out onto a basinal erosion surface, which you can see in core. You don't have to see the whole outcrop. And usually you don't see a lot of bioturbation because these dunes are building up fairly rapidly. To identify ripples, they're either going to be unidirectional or bidirectional. They're usually stacked like the ones that we see here, and more often they occur in finer grain beds as well. And then as far as lateral accretion surfaces go, so to identify point bars, they'll be steeply dipping, but they can be shallow, but they are usually fairly continuous. So this is these lateral accretion surfaces sitting in here. They may have bits of mud associated with them or mud drapes, and they might either be sand dominated or a mix of sand and mud. So let's look at some other terrestrial settings now. We're going to start off with aeolian or wind-blown deposits. And these form usually where vegetation is sparse or absent, and usually where things are very dry. And the classic example is these wonderful dunes that reach up to about 400 meters in height, which you find in Namibia on the Walvis coast, on the Namib-Naukluft National Park. And these are incredible structures. So what do they look like when you get inside? Well, when you get inside, you can see that they're composed of these giant stacks of crossbeds here. And the biggest crossbeds in the world are found in aeolian wind-blown dunes. So there are three main desert settings on Earth: alluvial fans, which we've already talked about, sabkas and playas, which is the lakes that occur in between these giant dunes, and then the sandy deserts with the giant dunes themselves. And then you do also see some erosional features. We're not really going to talk about those, but if you want to try and recognize these in the fossil record, first of all, they're usually red because they're basically, when you see red sediments, that means they iron oxide has rusted away. So any iron that's in the sediments has rusted away to create the red color, which only happens usually in terrestrial settings. They have very well sorted, pitted, frosted grains because the grains have been blown around and blown over each other, and they've aggraded each other. And so you tend to see this frosted surface. They have very thick crossbed sets with very high angle foresets. So normally the maximum angle of repose for sand is about 35 degrees in these. But normally, if you look at things like deltas, you don't see anything quite that steep. And then you should look for polished faceted pebbles as well. So this is a classic dune from Horseshoe Bend in Arizona. And what you can see here is that you've got a coarser layer at the base, and that's why it's got this darker color, because it's actually soaked up some water. And then overlying that, you have these beautiful giant crossbeds here. So they do look a bit like trough crossbeds, but the difference is you have this bright red color here. You don't see a lot of overbank mudstones. It's really just pure sand on sand on sand. While we're talking about terrestrial sediments as well, I just want to mention a couple of other sedimentary structures that you may come across, which are raindrop impressions. And these ones here, I don't have any nice fossil ones to show you, but these are recent ones that I captured on film a few weeks ago in a building site, and some nice mud cracks as well. So when sediments dry out, they develop cracks, and then the cracks fill up with sediment, and they can be preserved as mud cracks. And these are examples here from the Isle of Wight, on the south coast of the Isle of Wight. You can see these beautiful mud crack arrays here with some of them are up to a couple of centimeters in width, and that depends on really the thickness of the crack itself. So just to summarize for aeolian and desert settings, I've got 3 cores here that I actually, they're all from North Sea reservoirs, and I bought these cores from a nice core charity in the UK that saves cores when they're going to be thrown away. And what we have here on the left is a possible alluvial fan deposit with poorly sorted conglomerates that we saw earlier on when we were looking at those sediments from Devon. We have beautiful pink planar cross-bedded sands here, where you can see at the base here we have slightly muddier sands and flat lying, which would be the interdune deposits. And then overlying that, we have a lovely sand dune with the pink coloration. And my analog here is from the Great Sand Dunes in Saskatchewan, which were deposited in glacial times. And then finally, you have the Playa Lake deposits. So that would be like the base of Death Valley, where you have these wavy laminated sediments, a mix of very fine-grained sandstones and possibly silts as well. And once again, the reddish color gives us an idea that this is a terrestrial setting, plus it's interbedded with dune deposits as well. So that association helps us to sort out what's going on. And I just put this in because it's beautiful. So this is an example of a giant sand dune that was blown against the side of Majorca when the sea level fell to 0 in the Mediterranean. So about 5 million years ago, we had a Messinian salinity crisis. The Mediterranean was basically dammed off at the mouth, and the whole Mediterranean dried out. And giant dunes were blown across the base of the Mediterranean and blown up against the side of Majorca. So this is about a 50-meter high sand dune in Majorca. And on the surface of some of the bedding plains, you can see these beautifully preserved antelope footprints, 5 million year old antelope footprints. So just before we finish with terrestrial, let's talk about lakes. And I'm not going to, there's lots and lots we could say about lakes. They can have deltas in them. They can have turbidites. They can have all sorts of features in them. But for our purposes, the most likely thing that we're going to see is varves. And varves are yearly cyclic deposits, and they're stripy in character. So this is from glacial Lake Calgary, which is about 10,000-year-old sediments. So at the time in the last ice age, basically Calgary was dammed off from the Rocky Mountains and a huge lake formed in the Calgary area. So where I'm sitting here in Calgary, I would have been under about 60 meters of water. And you can see that you get these stripy black and white deposits being built up through time. There are also sandy deposits you see in glacial Lake Calgary as well, but for our purposes, let's just concentrate on these varves. And these varves usually are millimeters in thickness. These ones here in Calgary, this is quite rapidly deposited, so they are centimeters to decimeters in thickness, which is really quite thick for varves. So let's move on to estuarine and tidal settings now. And it's a bit of an overwhelming topic, this, because this diagram here just shows all of the different environments that you might come across in your estuarine setting. So there's an awful lot of them. So if we summarize those, we've got the major channels, rhythmites, herringbone cross-stratification, tidal flats, lagoons, mangroves, and mouth bars. So first of all, let's sort out lagoons. So lagoons are mainly muddy in character. They tend to evaporate, so you end up with hopper crystals or salt crystals. And this example here, which is from 1500 million years ago, from Waterton National Park, each of these little squares here is a separate hopper crystal. And then this example here from the UK, from Dorset, this is an iguanodon footprint, and on this surface are lots of hopper crystals as well. So this iguanodon walked across a saline, evaporating lagoon and left his or her footprint there as well. And then as far as mangroves go, I could talk about mangroves all day. It was part of my PhD study. But for your purposes, if you're going to recognize fossil mangroves, the thing to look for is these very striking rooted character. So the roots will go down through the sediment. They're very interesting because they make the vertical permeability very, very high. So they're good reservoir deposits or good for carbon sequestration. But yeah, the best thing to look for is these rooting here. And if you don't see a lot of rooting, don't worry too much about it, whether it's a mangrove or not. So let's start off on the biggest scale. So the biggest scale in an estuary is the estuary itself, the large scale channels. And the estuarine channels can be sand fills, which will be almost certainly dominated by trough cross bedding. And this is an example here where you can actually see some of the large troughs in this sand-filled channel. They can be heterolithic, so they can be in this inclined heterolithic stratification. So just the same as the point bars we talked about earlier. These are estuarine point bars. And look at this beautiful example here. Hundreds of meters of this exposure here, all showing these inclined heterolithic beds. Or they can be mud-filled. So the same kind of oxbow lake that we saw in the terrestrial setting in Dinosaur Provincial Park. This is from Drumheller in a tidal setting, where you can see in this lower right-hand diagram that we have this nice mud-filled channel sitting there as well. So really, a little bit difficult to tell these apart from river channels. So you really want to look at what's associated with these beds before you confidently say that they are estuarine. So some of the things that you're going to see are mouth bars. So the mouth bars occur at the kind of mouth of the estuary. So this would be a river coming down in a deltaic setting, the estuarine channels here, and the estuarine channels will be building out onto the delta front. And what you can see is that at the front of the rivers or the distributary channels, you start depositing these mouth bars here. And these mouth bars are sandy deposits. Here's a really nice example from Utah. And you can see that they have this dipping cliniforms through them. So if you follow any one bed down, it starts at the top of the bed over here, and it gradually makes its way down throughout the mouth bar as you move laterally. And I did say I would mention carbonates. This is a carbonate mouth bar from Majorca. So this will be associated with those mangrove deposits we saw. And once again, you can see these dipping cliniforms within this mouth bar deposit. So the way to recognize those is this really tabular dipping cliniforms in a deltaic setting. Another tidal feature that you see are rhythmites. Rhythmites are where you have changes of current through time, and that's obviously tides, proximal tides, distal tides. As the tide moves in and out, flowing in different directions, it will deposit a mud, and then a sand, and then a mud, and then a sand. And this bottom right-hand diagram here is just showing these beautiful centimeter scale rhythmites. So that, as I put here in this green box, look for those rhythmic alternations of mudstones and sandstones. What you can also look for in tidal sediments is to look for tidal bundling. So this is an example of a dune that's building up through time on the left-hand side here. And what we see is that where you have the lowest tides, the tides with the least energy, you deposit the thickest muds. And then as you go through the tidal cycles, what you'll see is that the deposition rates thicken and thin through the month. So you'll end up, you should be able to count off 28 different cycles in here with the high to low tide throughout these cycles going from neap to ebb right the way through. So you can actually count them out and make sure that you've got a tidal setting that you're looking at. This top right-hand diagram here is an incised valley fill from eastern Borneo. So this is Miocene in age. And what we see here is that we've got lots of stacked tidal channels, and each of those tidal channels is filled with these rhythmites. And just to take a step back, what we see here is that same estuarine incised valley. So the green is mudstones. So this is underlying. You have the mudstones sitting in here. Then you've had this big incised valley that started filling it up. The base of the incised valley is sandy, so that's the yellow fill here at the base. And then after that, you move up into these rhythmites. So every one of those channels, every one of these channels that you can see here on the top diagram is all picked out by the rhythmites. Another classic tidal signature that you might see is herringbone cross stratification. And this is another feature that relates to the fact that tides go in and go out. They go in and go out. They fluctuate, they go in different directions. And that leads to these alternating sets of little ripples here that are dipping towards the coast, away from the coast, towards, away from the coast. And that is called herringbone cross stratification, another classic tidal signature. Right, now we're going to move on to deltas, and that deltas are another huge topic, and we're not going to go into too much detail, but there are various kinds of deltas, river-dominated deltas like the Mississippi. We have tide-dominated deltas like the Ganges, wave-dominated deltas like the Rhone, and then the original delta in the shape of a delta, which is the Nile Delta, which is not really, it's wave influence, but not really affected by waves as much as some of the others. So depending on what your overall depositional regime is, will affect the shape of your delta. But within that delta, there are structures that you can look at in more detail, which help you to identify that it is a delta. And this is a little bit like mouth bars, but what we see here in a delta is the delta will build out through time. So these red lines in the upper right-hand photograph, those are cliniforms as the delta is building out into the sea towards the right-hand side of that photograph. So the bottom photograph is just showing a step back picture where you can see the whole delta, and then we're looking in more detail at the delta. And what we see within the delta is that we have these big cliniforms in the middle. Those are called the foresets. We have bottom sets where those beds flatten out, and we have top sets at the top of the delta where those beds flatten out as well. So if you want to try and identify a delta, you should be looking for flat top sets, dipping foresets, and flat bottom sets. And that combination of those three characteristics should be able to help you identify the delta. And what you'll also see is that underneath the deltaic deposits, so below the bottom sets, you should be seeing mudstones, because the mudstones are deeper water and the delta is building out over those mudstones. So I've got an example here from what I call the Inglewood Delta. So this is a little storm outflow near my house. And you walk down, there's a canal there, and you can see that here is a little pipe that's feeding out, delivering the storm water that's being deposited up here on the higher areas. It flows down, into the canal. And for my purposes as a sedimentologist, it's built a small laboratory for me to go and visit here along the river. So along the canal, I mean. So you've got mouth bars in here, really beautiful mouth bars, and you can see them here in this diagram as well. So the whole delta is only about 20 meters across, but we can see nice mouth bars there. We can see the distributary channels that are building their way out there. And then we can even see little cliniforms here, these little muddy cliniforms on a centimeter scale. There's my finger for scale. And that's in a hole that I dug just in this area here in the middle of this little delta, this little artificial delta. So as I said, deltas can be river, tidal, wave, or storm dominated. And this will affect the 3D architecture. But what we're really looking for here is flat tops and bases and the steeply dipping cliniforms in between and overlying the muddy deposits. And then this is a classic kind of delta succession here, where the delta's building out over the top of these muddy pro-delta and delta front deposits. Meanwhile, just along the coast from there, very similar, on the beach, we also see dipping cliniforms. So these are dipping, low angle, dipping beds that dip down towards the sea. And you have to be a bit careful with beaches, because anyone who's ever been to a beach in summer and winter, it changes dramatically, because in the summer, gradually everything's worn away and the sand is removed from the beach. And in winter, usually it's all pushed back up again. So you'll see a very different characteristic cross-section through a beach in winter or in summer. One of the ways to be sure that you are in a beach setting is to look for wave ripples. So on these surfaces here, these cliniform surfaces, you should be able to see wave ripples. And then hopefully you can see marine trace fossils as well. And I put my crib sheet here that I usually put in my field notebooks, where there's all the different types of shallow marine trace fossils that you might come across. So if you start seeing any of these, some of them are very familiar to us, like thalassinoides. Some of them are less familiar. Thalassinoides is basically the shrimp burrows that make up the flints that we see in the chalk. Some of them are less familiar, like Paleophycus. But all of these you should be able to find in these shallow marine settings. And we're going to look at some more shallow marine settings as we carry on with the presentation. And here we are. So in shallow marine settings, there is a very predictable series of sedimentary structures. So what happens is, once again, our shore face deposits, our coastal deposits, are building out through time. So at the base of your succession, you have the most distal, fine-grained, low-energy deposits. So that would be this offshore bit of this photograph from the Book Cliffs. We pass up into the lower shore face where we're starting to see sand. So that is the storm wave base, that's called, that line running along there that separates from the offshore. That's at about 75 meters water depth, and that's where storms start impacting the seabed. We have a storm-dominated succession down here in the lower shore face, and then we get to fair weather wave base. So this is where, in normal fair weather conditions, where the waves operate down to, which is probably about 20 meters water depth, and above here we're in the upper shore face. And in terms of the sedimentary structures, we go from thin distal storm beds with hummocky cross stratification, which I'll show you in a minute, up into swaly cross stratification up here, and then into trough cross beds where we're seeing longshore drift along the coast. So wherever you are in the succession, if you just drop me somewhere and you say, "Where are you, John?" by looking at the sedimentary structures, I can give you an idea of roughly what the water depth looks like. And if you want to see what that succession looks like in outcrop as well, in more detailed scale, this is about a 6-meter section here through the Cardium Formation, which is Cretaceous, very good oil producer, thinner beds at the base, thicker trough cross-bedded beds at the top. And the trace fossils actually change in character from Zooficus at the bottom up into Rhizocorallium at the top. So you have different trace fossils because the water depth is different as you go through that succession. So these are the sediments that you're likely to see. At the bottom, you see hummocky cross-strat. So this is the hummocks here with these convex up structures. So that's only seen in hummocky cross beds. So if you see convex up in core or an outcrop, you know you're in a storm setting. So you know that the water depth is likely to be probably more than 20 meters. You go up through the succession and you start seeing just the swales preserved. And the way you can tell these from trough cross beds is that they're thinner here at the edges of the smiles, and thicker as you go down into the kind of the core of the smile, and then thin out to the other side as well. So those are called swaly cross stratification. And then you go up into the upper shore face with these trough cross beds, longshore drift, and you'll see these lovely wave ripple surfaces on the top of each of those sandstone beds. And then the other thing you might see in the more distal deposits, the storm deposits, is that you might see these gutter casts as well. So these are the characteristics, I've already mentioned them, that will help you to identify each of those settings. But what you should be looking for is convex up. You can immediately say we're in a storm setting here. And those hummocky cross stratification, that was only recognized in the 1970s, so it hasn't been around that long. So this is just an example of hummocky cross stratification with a younger version of my daughter for scale. And you can see these beautiful beds here. They're thickening and thinning laterally, and boudinaging as well. And this is all because we've basically got a seabed that's being pummeled by storm currents. And this is just one example of one of these coarsening upwards cycles. So in our shore face, we go from distal, fine-grained, to proximal, coarse-grained. So we coarsen up through time. This is what the succession looks like. It's 53-meter succession through here, going from interbedded silts and muds up into sands, and the sands coarsen up through time. And this is a gamma ray, handheld gamma ray that we took across this outcrop as well. And that shows you the same characteristic. Muds at the bottom, sands at the top. This is what it looks like in outcrop. So we've got muds at the bottom there, and we gradually coarsen up into sands. And the sort of sedimentary structures that we're seeing is in the lower part, we're seeing this hummocky cross stratification with the beds thickening and thinning. And then we have wave rippling towards the top here. You can see these symmetrical waves that we're seeing on the top of this sandstone bed. And then in the deeper water, we're seeing starved ripples. So that would be down in this portion here, the right-hand side of the diagram, where we're seeing only enough sand to fill in the sort of troughs in the ripples. We're not seeing enough to have a complete sand layer, just isolated little sand ripples. And then this is just to show what it looks like in a big outcrop here. This is all storm deposits. This is from Grand Cache in Alberta. And we're seeing these stacked storm deposits with these lateral variations in the thickness of the sand bodies due to the pummeling of the seabed by storms. I thought I should mention these for the sake of completeness. So we have a lot of sand waves offshore the UK. That's what they used to be called. They're now supposed to be called compound dunes. And what they are is that they're basically stacks of dunes upon dunes. And these are tidally related. So when you have strong tidal currents, they will move this sand across the seabed and they'll create these basically giant ripples. But these can be up to tens to hundreds of meters in length and up to 20 meters in height. And you can even get tidal sand ridges which are even bigger. And I've got an example from Core here, which is basically stacked trough cross beds from the Quest project. So this is a carbon sequestration project here in Alberta that's going on near Edmonton. And then you can see with the tidal bars here, we've got these cross beds sitting in here. And then what you'll see is more and more trough cross bedded dunes that actually ride over the basal dunes that you're seeing within the main core of the bar. While we're in this point of the talk, we just mentioned a little bit about dewatering and sand dikes, because I said I'd talk about deformation structures. So we've talked a lot about deposition, depositing sand. These ones here are deformed. So when they were deposited, these sands were very water laden, and the water was basically squeezed out of them, and it folded all of the sediments up as well. So you can see all these little folded bits of sediment sitting in here and in here. You can often get a trigger, which would be a seismite. So a seismic earthquake or something like that will activate the seabed, and it will tend to promote this and make this happen more readily. I've got an example from the sky as well. These mammatus clouds here, these are also foundering, where you've got sediment that's actually foundering down into the underlying mudstone, in this case, the underlying air, because these are laden with water droplets. And then you also see sand dikes where you squeeze the sediment. If you have a crack in the sediment, then sand and water can be remobilized and it can deposit sand as a dike. So it's not an igneous dike, this is a sand dike, and they're all caused by dewatering. So we're going to finish off by looking at deep water settings. So the most famous deep water deposits are turbidites. So these are where downslope currents erode into the seabed. So they basically start off by eroding. So these are erosive structures here, which are these grooves, which are caused by bits of sediment being dragged across the seabed by these turbidite currents. We also see lode structures where we have sand deposited very rapidly on the seabed, which tends to sag down into the seabed and create these lode structures. And we see flutes as well, which are another kind of scouring feature that we see at the bases of turbidite deposits. And we can recognize these turbidites also by what's called the Balmer sequences, named by Arnold. Well, he didn't name them, but he talked about these sequences. Arnold Balmer, who is a Dutch geologist, he identified these in the first place. And this is a complete Balmer sequence here with massive sediments at the top, planar beds, rippled beds, upper parallel laminae, and then up into a mudstone at the top. You don't always see all of these parts of the succession, but if you see this succession, you can be confident that you're in a turbidite setting. And then also associated with these deep water deposits, we see slumps and slides and canyons as well. So this is a submarine canyon on the lower right here. So if you see mudstone deposits with this deep water trace fossils in them, and then we see these sand bodies within them, then that's almost certainly a canyon fill. And then we see these extraordinary deposits here, which I'm hoping to see next month when I go to Tokyo to run the marathon. These are still exposed just outside Tokyo. So I'm hoping to see these, which are big slump box, which have been moving down the depositional slope in a deep water setting. And we can recognize these deep water settings partly by the extraordinary trace fossils. We've got Paleodictian here on the right, the very famous hexagonal sort of beehive-like setting. And then we have these very complex cosmoraphy, what are they called? Meandroglyphs, graptoglyphid trace fossils sitting in here as well, which are feeding traces. So just to summarize, we've seen how sedimentary structures can be used to determine depositional settings. And like everything, don't be overwhelmed. It gets easier with practice. Start off by reading about the outcrops that you're going to go and see, so you know what other people think of what those deposits are, and so that other people understand that they've already looked at the sedimentary structures and interpreted them. And then you go there armed with a bit of a cheat sheet that will help you to know what to look for. Many textbooks have more information. There's lots of textbooks about sedimentary structures. There's one by Nigel Mountney and John Collinson, which is really good. That's reasonably priced as well. I haven't talked about trace fossils today. It's for another day, but they are a very useful tool when you're trying to interpret your depositional settings. And I just want to wish everybody good luck with identifying your sedimentary structures. I'm going to finish with this just to show some of the animals that I've come across in the field in the last couple of years. that black bear in the middle was actually on the outcrop that I was supposed to be looking at for work. And we are sitting comfortably in a truck at that point, I have to say, while he's wandering around, although I don't think he was dangerous. And the other thing that I put here in the presentation, just as a little guide for all of you, is a summary table of sedimentary structures. So I put this together particularly for this talk. I've never done this before, but it was quite a fun thing to do, to think through how you recognize all of these different structures. So everything I've talked about today, pebble bars, trough cross beds, planar cross beds, they are all on these 3 tables here. So that also gives you another tool that you can use when you are trying to think about what depositional setting you might be in. Okay, I'm going to finish there, and I'm happy to take any questions.
Thank you, John, very much. That's just amazing.